Okay, let's dive into this. We're talking about deep learning, the powerhouse technology that's kind of become the engine behind our entire modern world. It's literally the magic in your smartphone's camera, the smarts behind your web searches, and so much more. But how does it actually work? Believe it or not, pretty much everything you need to know is packed right into this one sentence. It's from the three researchers who basically invented this field. Now, it sounds a little dense, I know, but we're going to unpack it. Because getting a handle on this one idea is the key to understanding one of the most powerful technologies of our time. So, to really get why deep learning was such a big deal, we first have to understand the old way of doing things. You see, for decades, machine learning systems, even the smart ones, weren't really learning on their own. They kind of needed a human to hold their hand. And this, right here, shows the fundamental shift. See, with the old school approach, if you wanted a machine to recognize a car, a team of brilliant engineers had to sit down and painstakingly code what they called features. You know, things they thought were important, like the shape of a wheel or the reflection of a window. Deep learning just flips that whole script. You don't tell it what to look for. You just show it a million pictures of cars, and it figures out the important features all by itself. And this really gets to the heart of it. The real breakthrough isn't just that the machine is learning. It's what it's learning. It's learning how to represent the data. The machine figures out the best way to see the world all on its own. That autonomy, that ability to learn from raw data is the single biggest advantage, and it's the engine that kicked off the AI explosion we're living through. Which, of course, leads to the really big question. How on earth does a machine learn to see patterns without being told what they are? Well, the answer is right there in the name, deep learning. The secret is to go deep by learning in layers. Think about it like building something with Legos. The very first layer looks at the raw pixels of an image, and it learns to spot only the simplest things, like a horizontal edge here, a dark corner there, maybe a patch of blue. Then, the next layer doesn't see pixels. It sees the first layer's work. It takes those edges and corners and learns to assemble them into slightly more complex shapes, like an oval that might be an eye, or a curve that could be part of a tire. Then the next layer combines those parts into bigger things, like a whole face or a car door, until finally, the top layer takes all those assembled parts and confidently says, yep, that's a person, or that's a car. Each layer builds a more abstract, more complex idea. Okay, but wait a second. This whole Lego building process is great, but it would be totally useless if the network couldn't get better, right? It needs a way to check its own work and actually learn from its mistakes. So how does it do that? The secret sauce here is a really clever process called backpropagation. Here's the analogy. Imagine the network's mistakes as being in a big hilly landscape. The goal is to get to the lowest possible point in a valley. That's the point of zero mistakes. So after it makes a guess, say it calls a cat a dog, backpropagation calculates the error. It then figures out which way is downhill and sends a tiny correction signal all the way back through the network, telling every single layer, hey, you need to tweak your internal knobs just a little bit this way to get us closer to the right answer. You do that thousands, millions of times, and the network slowly, step by step, walks its way down into that valley until it gets things right almost every time. Now, while that layered approach is the general idea, you need the right tool for the right job. And when it comes to vision, teaching a machine how to actually see, the massive breakthrough came from a very special kind of architecture, the convolutional neural network, or what everybody just calls a convnet. Convnets were actually inspired by our own brains, by the human visual cortex, and they use a few really smart tricks. Instead of trying to look at a whole giant image at once, its neurons only look at small patches. And here's the really genius part. It uses the same exact feature detector, say one that's good at finding a vertical line, and scans it across the entire image. This idea of shared weights is incredibly efficient. Then it just stacks these layers, building up that hierarchy we talked about, from lines to corners to textures to eyes to faces. And the result of all this? Well, just look at this number. In 2012, a convnet was entered into the ImageNet competition, which is like the Olympics for computer vision. It didn't just win, it absolutely demolished the competition. It slashed the error rate by almost half compared to the next best thing. This wasn't just a win, this was the shot heard round the world for AI. It was the moment the modern AI revolution truly began. And that 2012 breakthrough wasn't just some academic thing locked in a lab. Today, that exact same fundamental technology is in your pocket, powering the face recognition on your phone. It's in hospitals, helping radiologists spot tumors in medical scans. And it's the core of the vision systems in self-driving cars. But hey, the world isn't just a collection of static pictures, right? What about things that unfold over time, like speech or text in a book, or a piece of music? For that, you need a different kind of network, one built for sequences, the recurrent neural network, or RNN. The magic word here is memory. A ConvNet looks at an image all at once, in a single forward pass. An RNN is different. It has a loop. It processes one word in a sentence, and then that loop allows it to feed a little bit of information back to itself before it processes the next word. It's like when you read a sentence, you remember the beginning to understand the end. That internal loop gives the RNN a memory, a history of the sequence so far, which is absolutely essential for understanding context. And here's where it gets really wild. As these RNNs learn a language, they don't just memorize words. They create these rich mathematical representations. People call them word vectors that actually capture the meaning of the words. It's like building a map of concepts. And on this map, words with similar meanings are located close together. So the vector for Sweden is right next to the one for Norway, and Tuesday is right next to Wednesday. The network is learning the relationships between ideas. So this is where you combine the two and things get just mind-blowing. Researchers hooked up a ConvNet, the eyes of the system, to an RNN, which acts as the mouth. The ConvNet looks at an image and figures out all the objects and actions. It then hands that information to the RNN, which translates it all into a natural descriptive sentence. This was just a stunning moment. It showed a machine that could achieve a deep, two-part understanding of the world. It could both see and describe. So all of this incredible progress brought the whole field to this major turning point around 2015. With computer vision and language pretty much cracking open, the pioneers of the field started looking ahead. They asked, okay, what's next? What's the next great challenge on the horizon? And looking out from that moment, they saw three huge frontiers. First, the holy grail of unsupervised learning, teaching machines to learn just by observing the world, the way a baby does, without needing millions of labeled examples. Second, they wanted to push deep reinforcement learning, where an AI learns complex skills just through trial and error, like learning to play a game. And the ultimate endgame? Combining these amazing pattern recognition machines with the ability to perform complex multi-step reasoning. And that brings us to the final provocative question that researchers are still wrestling with every single day. We have built machines that are incredibly, almost spookily good at intuitive pattern recognition. But how do we bridge that gap? How do we get from just learning patterns to the kind of flexible, common sense reasoning that we think of as true intelligence? That remains the grand challenge.